Good evening, all. Let me share the screen with you first. Please confirm whether the screen is visible or not and whether I am clearly audible or not.
Yes, screen is visible and you're audible.
Okay, thank you for the confirmation. So today we are going to discuss one of the very important topic with statistics, which is multivariate analysis, and I am going to start with principal component analysis, that is PCA. Okay, so let us start. Multivariate analysis, and we are going to start with PCA. Okay, so the basic thing of PCA we all know. Still, I am just revising the basic part corresponding to PCA. What is actually PCA? Principal component analysis. Why this method is used in multivariate analysis? Number one, why this method is used. Number two, when this method is used. So first we should start discussing in a reverse order, that when this method is used rather than why this method is used. So when and why almost gives you the similar answer. So suppose we have a multivariate data set. Suppose we have a multivariate data set, and in this data set, the size of the data set is n, and which is very large. And it has actually, suppose we are trying to fit any regression or multivariate regression on it, or whatever we are trying to do, and suppose it involves p covariate. Just we are telling that it involves p covariate. Okay, so now, but thing is that sometimes it happens that it's very difficult to deal with such big data set. We in real life, all the data sets are not of like size. We say that in statistics, if n is greater than equals to 30, the data set itself is very big. But in real life, basically the data set is always greater than 30, not exactly equals to 30, but it is actually much greater than of the exact size 30. So when we say that it is very large in size, that my actual data set, then we it's very difficult to represent this particular data set, and it's very difficult to deal with this particular big data set. So what we try to do, we try to like represent this data set in a lower dimension. So for dimension reduction, this PCA is a very important tool. Okay, so first of all, let us see that how we can use this dimension reduction. I'm not going into the proof and all those things. Okay, so we wanted to see what is the main objective of PCA over here. So the main objective of PCA is actually is to reduce the dimension of the data. Number one, this can be done like considering only some of the components of but like after doing this principal component analysis, but that may lead us to some problems as well. So let us discuss that things over here. So let me draw this. Suppose this is my data cloud. Suppose this is my data cloud basically, and we have a component L2 curl over here, and this is called my data cloud. Okay, this is my x2, this is my x1. So what is the spread of the projected points based on this L2? The spread of the projected points based on this L2 is basically this portion. This we can say it as spread of the projected points based on L2 curl. Okay, so consider this as my figure 1. Now going to the figure 2, also x1, over here x2. So this is again the data cloud. Okay, and here the line of projection is, suppose, say this one. This is my L1 curl. I should have drawn this first. That's why it is L1 curl. This is figure 2. And if you can see the projection over here, sorry, the projection over here is between these two lines. Let me indicate the lines over here. Here is this one, and this one. This point and this point, and basically it is connecting these point and this point. So it is going to connect this point and this point. So let me draw a line connecting this point and this point. So this is what? This is nothing but the spread of the projection, or the projected, I should write projected, based of the projected points based on L1 curve. So as you can see, whenever I am changing the projection, like L1 curve and L2 curve, these two vectors, the spread is actually changing. So that's why this PCA, this like involves problem of choosing the direction of L curl as well. So one of the major problem over here is choosing direction of L curl. You all know what L curl is in PCA. I'm going to discuss the formula, but this is the problem, like the direction of L curl. This is one thing what we need to discuss because of that one reason. And one another reason is like how much variability is, which all we all know, how much variability. Reason number 2, how much variability is like covered. How much variability is covered? This is my question number 2. And last thing is like the target of PC ultimately to cover this thing is my dimension reduction. Okay, is it clear? So for
Yes.
this thing, what mathematically we actually going to do? Mathematically, it's very simple. Suppose we have a particular data set, and we are actually like writing the data set as this capital P, capital X, which we are writing as P cross 1 X curl. We are saying that it's a P cross 1 random vector. We are saying that it's a p cross 1 random vector. So basically if it's a p cross 1 random vector, then what are the features of this thing? The dispersion of this x curl is my sigma, which is greater than equals to 0, that is PD matrix. And we are taking a transformation. This is very important. We are taking an orthogonal transformation from x curl to u curl. What will be the transformation? The transformation is u curl is b transpose x curl. What is my b? Where my b is a vector, will consist of, it's a matrix whose columns are vectors beta 1 curl, beta 2 curl, beta p curl, where beta I curl are characteristics vectors of this sigma. So we are actually focusing on this. We are concerned about the characteristics root and characteristics vector of this what do I say, this matrix sigma. Okay, and what we are saying that the characteristics roots, just a minute, the characteristics roots of this sigma are assumed to be like this lambda 1, lambda 2, lambda p. These are the characteristic roots of sigma, and also we are assuming without loss of generality that this lambda 1 is greater than equals to lambda 2 is greater than equals to lambda p is greater than equals to 0. So we are assuming that they are actually ordered. So this is the scenario and we are taking the transformation. After taking this particular transformation, you know that the characteristics roots and characteristics vectors, that's corresponding to basically my eigenvector and my eigenvalues. Okay, so after that, what we are actually doing, so basically this transformation, the that is ui corresponding to some beta I curl transpose x curl. Okay, this is actually called my ith principal component, ith pca, sorry, ith pc, not a, IFPC, ith principal component. What it actually do and how, in this way, basically, since we are dealing with like I running from 1 to n, we are dealing with this 1 to p, sorry, we are dealing with this p component, like x is of order p cross 1. So we are going to get u1, u2, up in such way. So corresponding to like x1, x2, xp, after taking transformation x1, x2, xp, from this set we actually have got, after transformation, this set u1, u2, up. So the problem is that the dimension is not reduced. Okay, so these are my pc components. So dimension is not reduced. Till now the dimension is not reduced, just this has been done with an orthogonal transformation. Just an orthogonal transformation mentioned earlier, this has been done. Now after that, how I am going to select, but what is the problem of these two set is, like for this case, this is actually my data set where I am not sure that what to use, what not to use. So I have this full data set, but this has been transferred to some PCs, principal components, where I have the liberty to choose some of the components based on some terms and conditions, which is actually going to give me the liberty to choose, like out of I can choose some of the components which will reduce my dimension of the whole data set. This is my p dimensional data, and I have the liberty to choose some of the components which may be less than p, obviously, which is going to be less than p. Suppose I am choosing some q components which obviously going to be less than p, and these q components will be sufficient to represent my data. But what is the condition that when I am saying that this q components will be sufficient, and how I am going to choose this q components? What the criteria of choosing this q components? So two questions: how to choose q components, how to choose this q less than p components. I should write less than equals to p. It maybe sometimes it doesn't reduces the reduction, but most of the cases q is less than p. But this is the bound basically. How to choose these components, and like how we are going to choose, like components means criteria I am talking about. And how to judge that those Q components are sufficient or not. So to answer these two questions, we need two things. So first, we are going to discuss about this particular portion, which is totally mathematical. What is this particular portion says? If ui is the ith principal component, that which we have already discussed. So let us take my first principal component, my first PC, u1. Okay, so u1 has the we assume by default, like the orthogonal transformation, where this beta is my eigenvectors, where my lambda 1 lambda 2 are my eigenvalues. So by default it says that this u1 is has the maximum variance among all other normalized linear combinations of x curl. So what features u1 has? It has max variance among all other normalized linear combination of x curl. Okay, so this is my first component u1. So that means I am at least going to choose one component. This is for sure. So u1 is obviously going to be chosen. So u1 is sorted out. So whether I need to choose u2 or not, obviously I this is the whole data set, and my main target will be for dimension reduction. Main target will be dimension reduction over here. So whether I need to choose this U2 or not, what will be the criteria? U2 is my second PC, second principal component. U2 has the maximum variance. U2 should also have the max variance among all normalized combination of X curl which are uncorrelated with U1. That point is very important, which are uncorrelated with U1. That means U2 should be independent of U1, because whether we need to choose this Q components or not, so let us write that Q independent components. And here also Q independent components. Because we are saying that once U1 is chosen, whether U2, if U2 is correlated with U1, we can't choose U2, we will go for U3. And if U3 is not correlated with U1, we will choose U3. If U3 is correlated with U2, then we also can't choose U3 as well. So all the components should not be related to each other. So now what will be the criteria for choosing U3? I'm just going to show up to U3 only. This is my third principal component. It shows that it has max variance among all normalized linear combination of X curl which are uncorrelated with U1 and U2 both. So that is the main thing. It should be uncorrelated with U1 and U2 both. So if U3 is correlated with U1 but uncorrelated with U2, still we can't choose U3 because it is at least correlated with one of the previous component. So whatever component we are going to choose out of this P from the U1, U2, UP, this should be not correlated. So in this way we can write in a general manner up to like UP. This is my pth principal component, and we can write that this is going to give me the max variance among all normalized linear combination of X curl which are uncorrelated with U1, U2 and up to UP minus 1 all. That is, for this set, it should be uncorrelated. Previous all, it should be uncorrelated. Then only we can choose UP. So all the things should be like independent components. So like we don't need to like, are we need to choose all the P components? So how to choose this Q components where Q may be less than P or maybe less than equals to P? That problem we have sorted out and we have answered. But how to judge that how many components we have chosen, with that is we have taken to be this Q or R, whatever you say, is it like fruitful to, or is it like sufficient to represent my data set X? Because X was too large, it P was a very large number and we couldn't deal with P. So is it like sufficient to deal with the other any other less number of amount of principal components which can help me to deal with this thing? If the answer is yes, then how to judge that, how to check the adequacy of the principal components? So let us consider this like test of adequacy of PC, adequacy of principal components. Okay, so how we are going to check that? First of all, before I go for the testing procedure, let me discuss that how we basically think that how this principal component basically works. We actually take the proportion methods of this principal components, and then we discuss that okay whether it is applicable or not. So significance, like how this particular things work. Okay, I am coming to this test later. Let me discuss this particular thing, significance. Then parallelly we can discuss the test. Okay, so basically if my P is too large, then we can deal with it. So we wish to reduce the dimension. So if we want to reduce the dimension, so like we obviously try to replace this my X curl with fewer number of components. And like I am always writing one thing, maximum variance, maximum variance, maximum variance. So we know, like suppose we have variance of X curl, and we can write variance of L curl transpose X curl. Not sorry for this. And like suppose further, like we choose a L curl in such a manner. We choose L curl such that this variance of L curl transpose L curl is maximized. We choose L curl in such a way. But the thing is that it can be like, is there any other condition we need to impose? The question is yes. The condition is that L curl transpose L curl should be 1. Why we are imposing this condition? Because without this condition, any variance of sort of this kind can be arbitrarily increased by incorporating any constant c which is greater than 1. Suppose I am considering c greater than 1 and I am writing variance of c L curl transpose X curl. That is going to give me C square variance of L curl transpose X curl. So that is also basically this process is also maximizing variance, but this we don't want because someone may choose any C and can maximize the variance, but we need to maximize variance with such and such conditions, and this is the condition which we want to impose, that L curl transpose L curl is going to be 1. Okay, so this is the condition, how the result, this is the first significance of this result. Next is like how we are going to judge this thing, like what is this lambda 1 lambda 2 over here? We say variance of u1 is basically my lambda 1, okay, and variance of u2 is my lambda 2, and we say we proceed like this, and u1 obviously we know is my first pc. Okay, so it is basically my beta 1 curl transpose X curl as per my notations. Now, whether V1 is lambda 1 is sufficient or not, how to like how to judge the portion or the proportion of total variability explained by U1. So the proportion of total variability explained by U1 is nothing but lambda 1 divided by summation over lambda I, where I runs from 1 to p. That is, since we have p components, p principal components, and we don't know that what are these, like how many components are required, which are actually going to give me the answer of the second question over here. We are actually discussing this particular second question right now. Okay, so basically for this we are saying the proportion of variability, we want the maximum variability to be explained. So suppose we are so the method is very simple, we are trying to find out the proportion of total variability. Out of the total variability, what is the proportion, since variance of u1 is nothing but the eigenvalue itself and variance of u2 is nothing but the second eigenvalue itself. So we are doing just nothing for explain for the proportion of variability explained by my first pc, we are taking it to be lambda 1 by summation over lambda I. If this proportion is satisfactory, we stop and replace x curl by u1. Okay, so what is the procedure if this proportion is satisfactory? Then we stop and replace x curl by u1. Please note this particular line. We replace x curl by u1. That means the whole data set is replaced by a single component because this proportion is satisfactory. So now the thing is that I am just quoting this word satisfactory because what do you think by satisfactory? Suppose I say this proportion is 0.9, that means 90% of the variability is explained by one component itself. So I don't feel like taking other components, so I can stop over here. So I think that 90% is explained by a single component. I won't take the other component. So it's fine. So this satisfactory. So how many components are needed? That we are going to take care by this test of adequacy of PC, which I am coming actually, which will be my next topic to of discussion. So which x curl is actually replaced by only one component. So instead of dealing with, so here what has actually happened, here I can say that dimension reduction has reduced basically. Here dimension has reduced. How dimension has reduced? Instead of dealing with this whole x curl which was of order p cross 1, I am just dealing with a single vector u1, which is what is the value of u1? Beta 1 curl transpose x curl. This is a single, the first component only. But now if this proportion is not at all satisfactory, then what we can actually do if it is not satisfactory. Okay, so if otherwise we will go for the second component. So let me write it over here. If the proportion if the proportion is not satisfactory, then we seek for a second normalized linear combination. The thing is that if you have seen just very carefully, I have not mentioned the name of u2, because I just written that second normalized linear combination, because I have not checked the second criteria, which is actually saying that I just mentioned second normalized linear combination. Why? Because I have not checked for the second criteria, which actually says that the first, second, whichever component I am going to use at the second position, like if u1 already has given or has like covered a certain portion or proportion of the variability, but some more components are needed. So that means what? That means actually u1 has covered some portion of variability, some proportion, sorry, some proportion of proportion of the total variability, but another normalized linear combination, but seek for, let me write over here, but seek for another normalized linear combination, because, and I have not mentioned the name of u2 because we don't know whether it is u2 or not. So suppose without loss of generality, now I can write let it be u2. So without loss of generality, say my second normalized linear combination is u2. Okay, so obviously u2 is going to satisfy this. So covariance of this u2 comma u1, that is going to give me 0, where u2 is of the form L curl transpose X curl as well. Okay, this is going to be my second principal component. And how to judge that what is the total variability explained by u1 and u2 both? So we are going to judge the total variability explained by u1 and u2. Obviously, okay, let me write one more thing. Variance of u2 is lambda 2. Okay, so u2 is lambda 1 plus lambda 2 divided by summation over I running from 1 to p lambda I. Okay, that means what are the components we are actually taking care of, divided by the total, all the variance, the total variability. So this is what, this is basically nothing but my total variability. So this is the proportion. So basically the number of like what are the components we are taking, that much variability by my total variability. So let me like this total variability. Okay, so this is total variability, and if this proportion is satisfied, so let me write the conclusion again. If this proportion condition is satisfied. Again, I am just underlining and putting this word under quotes. Satisfied, then stop or continue the process. Okay, so this in this way we can take, and obviously we know that when and if we are continuing the process and in this manner, suppose we are getting some lambda 1 plus up to plus lambda p divided by summation over lambda I running from 1 to p, this is going to be 1. So that means the total variability, this is like the total variability is covered. So we want the maximum variability to covered with the minimum components. So what we want? We want max variability to be covered with minimum number of components, or minimum number of PCs I can write. With minimum number of PCs, I can write principal components, and all the terms and conditions are there with minimum number of things. And generally, this suppose this Q components, what I say, generally this Q is very less than equals to P, very less than equals to P. This is the usual case, and that's why we say that PCA is a dimension reduction technique. Is it clear? Shall I repeat anything? Is it clear?
Yes.
Okay, now going for the adequacy of these principal components. So I'm going for this testing procedure. This testing procedure said, theoretically, suppose we say that the first, like theoretically, we say uh, the first are components U1, U2, UR. These far are components. These are like these first principal components. Like what I say. Okay, so when we say first, our components will retain. We should retain, or let me write it. We say the first our components will retain if this lambda r plus 1 is equals to lambda r plus 2 is equals to lambda p is equals to 0. That means from the r, after the r components onwards, if the basically if the like all the eigenvalues are basically 0. Okay, so basically we are trying to say that from R onwards, all the eigenvalues will be my 0. Okay, so and in that, for this reason, when we go for any softwares or something, we actually like eliminate those eigenvalues which are exactly 0 or close to 0. Okay, so let us write. Okay, let me write one more thing as well. uh, Let me write this line. So we know that while we are doing the testing, and this is like the visualization and all the procedure we are talking about. But in real life, when we deal with a particular data, we really observe the sample counterparts of the components, which we are denoting as L1, L2, LP. Hence, our decision regarding the number of components to retain will be totally based on this L1, LP, L1, L2, LP. Hence, our decision of retain, what do I say, regarding, let me write like in this way, number decision regarding how many components means to retain 10 will be will be based on this L1, L2, LP. Okay, so this is the thing. So we are actually totally like doing this thing based on this sample counterpart, and we are trying to do this. So first, what we are going to do now, we are assuming that our components we are going to retain or not. So first, our principal components, what how the testing procedure works. Let us take this proportion of our components 1 to r lambda I divided by summation I running from 1 to p lambda I is greater than 1 minus delta. Okay, where this delta is can be taken as 0.05, or sometimes we can take this as 0.01. It's like 5% and 1% significance, how much like restriction you wanted to take. I am going to proceed with this 0.05, not with 0.01. This is another option you can take, and even other options are there you can take. So that actually gives me summation over I runs from r plus 1 to p, that is from those components, some of those components which we want to retain, divided by summation over I running from 1 to p lambda I is going to be less than delta. Just interchange and done the summation, because this is nothing but the process of summation, nothing else. Okay, so this is the thing, and we consider this function to be a function of lambdas. So this called function of lambda curl is less than delta. Now our decision is this function we called, this particular thing we called my f of lambda curl. Okay, so how we take the decision, we need to now go for the testing procedure. This is how we have derived the test statistics. So my testing is basically over here. H naught is f of lambda curl is greater than equals to delta against h1 f of lambda curl is less than delta, because we wanted to check that, because if basically my testing will be based on that, whether we are going to be happy with this r component, or in other words, whether we want to like retain with this r plus 1 components, retain the like r this r components, or like from r plus 1 onwards we don't need it, or we need it on or we want to take it or not. So this is the test statistic, and to get the observed value of the test statistics, obviously I will say that we need the observed portion of this f of L curl is summation over I running from r plus 1 to p of Li. Obviously, instead of lambda I am going to get the Li portion, which is the observed p of Li. So this is the particular thing which we have actually got. And my test statistics will be, it's very important, the derivation is not required, so that's why I am not going into the details. This L curl minus lambda curl will follow asymptotically, obviously since the data set is too large, so it follows asymptotically normal with mean 0 and to this, and this is called my Wilks lambda. You know the Wilks lambda test. So by both delta methods, we can actually sort out this problem and can solve it. Okay, so this is the actual testing procedure, and we know when what will be the rejection criteria. So by using delta method, we can simplify it a little bit, and then we can change the testing procedure as our normal testing procedure, and then we can find out the confidence interval and so on. Is it okay? Mhm. Is it clear? Any queries, anyone? Hope not. Okay, so we can go and check for some sums. Like maybe one small sum, we can go and check for PCA, how it works basically. So it's a very small sum I am discussing today. Let x curl be x1, x2 has dispersion matrix sigma equals to where rho is my greater than 0. So we need to find the point PCs. We need to find the principal components. Okay, so obviously if you can see, I'm just not going into the details of the calculations. If you can see, the eigenvalues of sigma are lambda 1 will be 1 plus rho and lambda 2 will be 1 minus rho, because you know that 1 minus rho square is the determinant, and when we equate this with 0, and this is going to give me this thing. So obviously rho is greater than 0 implies that lambda 1 is greater than lambda 2. So this is the order of the eigenvalues. Okay, and we need to find the corresponding eigenvectors. So I have already done this, and I am just sharing the result with you. The corresponding eigenvectors are: one is my beta 1 curl, which is 1 by root 2 of this, of two components basically, and beta 2 curl is equals to 1 by root 2 of 1 minus 1. These are the two principal components. These are the two eigenvectors, and these are the two eigenvalues. So we need to find the principal components. So we know the formula of PC. PC1 is my u1 is equals to beta 1 curl transpose x curl. That is going to give me beta 1 curl transpose x curl is going to actually give me x1 plus x2 by root 2, and u2 is beta 2 curl transpose x curl is going to give me x1 minus x2 by root 2. So obviously, if I tell you that, you can actually check that variance of u1 is variance of x1 plus x2 by root 2, that is equals to 1 by 2 variance of x1 plus variance of x2 plus twice covariance x1 x2. I said the principal components will be uncorrelated, but I never said that x1 and x2 would be uncorrelated. And obviously from this matrix sigma, it seems that it's very clear that variance of x1 and x2 are 1, because this denotes variance of x2, this denotes variance of x1, this denotes covariance of x1 x2. Okay, so basically we need to put these values over here. Half of 1 plus 1 plus 2 though, that is going to give me 2 plus 2 rho by 2, that is equals to 1 plus rho, which is my lambda 1. So it satisfies the theory which we have learned, and in a similar manner if we try to check variance of u2, it is also going to give me lambda 2. So in this way we can find out the principal components. So how much variability it is taking care of? Total variability is lambda 1 plus lambda 2. This is my total variability. uh, Let me add them. That is equals to 1 plus rho plus 1 minus rho, that is equals to 2. So proportion of variability by u1, I can take then take by 1 plus rho by 2. Proportion of variability by u2 will be 1 itself. So I need to check that whether this proportion is sufficient or not based on the testing procedure, taking delta to be 0.5, and then we can transform the test as I mentioned by using the delta method of multivariate and large sample. We can actually convert the test to the normal testing, and then we can use the tau. For asymptotic normal, we can convert the test to normal procedure of testing for large sample normal test, and we can actually do the rest of the procedure. Is it clear?
Yes. Yes, ma'am.
Any queries from anyone? Anyone, any queries?